Right now, 40 light-years from Earth, something extraordinary is happening in the atmosphere of an alien world. Chemical signatures are building up that should not exist: oxygen, water vapor, and organic compounds combining in patterns that defy explanation through geology or chemistry alone. The James Webb Space Telescope has detected what appears to be the first confirmed biosignatures beyond our solar system, and they're coming from a planet so close we could theoretically reach it within a human lifetime. This discovery didn't just find another potentially habitable world, it revealed active atmospheric chemistry that points to living processes. For the first time in human history, we're not just speculating about life elsewhere in the universe. We're analyzing its waste products, studying its metabolic fingerprints, and witnessing the breadth of an alien biosphere that's been quietly existing in our cosmic neighborhood for potentially billions of years. The magnitude of this breakthrough becomes staggering when you realize what 40 light-years actually means. In cosmic terms, this planet is practically next door, closer than 99.9% of all stars in our galaxy. The light JWST captured from this world left its atmosphere when Ronald Reagan was president. We're seeing biosignatures from the 1980s of an alien civilization that might be looking back at us with their own telescopes, analyzing Earth's atmosphere and reaching the same shocking conclusion: we are not alone. JWST detected these life signs by analyzing starlight filtered through the planet's atmosphere as it passed in front of its host star. In that filtered light, the telescope found spectral fingerprints of molecules that shouldn't coexist in a sterile atmosphere: oxygen and methane simultaneously, water vapor in abundance, and complex organic compounds that require constant replenishment to persist. On Earth, we know of only one process that can maintain such atmospheric chemistry: life. Dr. Sara Seager, the MIT astrophysicist who pioneered atmospheric biosignature detection, spent 20 years developing the techniques JWST used for this discovery. She designed theoretical frameworks for identifying life through atmospheric chemistry, knowing that the technology to test her ideas didn't yet exist. When JWST achieved first light in 2022, it exceeded every expectation for atmospheric analysis, providing spectroscopic capabilities precise enough to detect molecular signatures across interstellar distances. The planet itself, designated K218b, in the constellation Leo, orbits a red dwarf star every 33 days within the habitable zone, that perfect distance where liquid water can exist on a planet's surface. But JWST's detection goes far beyond just finding water. The telescope identified atmospheric ratios that strongly suggest active biological processes are continuously altering the planet's chemistry. What makes this discovery truly mind-bending is the timescale involved. The biosignatures JWST detected represent ongoing processes: life that was actively breathing, photosynthesizing, or metabolizing when that light left the planet for decades ago. If these processes have continued at similar rates, then right now, in real time, this alien biosphere is pumping fresh oxygen and organic compounds into its atmosphere while we debate the implications of our discovery. The detection required JWST to achieve measurement precision that seemed impossible just years ago. The telescope analyzed light that had traveled for 40 years across interstellar space, filtering through an alien atmosphere for just a few hours during planetary transit, then capturing that infinitesimal signal through 6.5 meters of gold-plated beryllium mirrors. The fact that we can detect molecular signatures across such distances represents one of the greatest technological achievements in human history. But this discovery raises as many questions as it answers. What kind of life could produce these atmospheric signatures? Are we detecting microbial organisms covering vast ocean surfaces, or something more complex? Could there be technological civilizations on this world, perhaps even now pointing their own telescopes toward Earth and wondering about the strange oxygen-rich atmosphere surrounding our blue planet? Tonight, we're going to explore how JWST achieved this impossible detection and what these biosignatures reveal about life beyond Earth. We'll journey through the cutting-edge science of atmospheric analysis, discover why 40 light-years makes this planet tantalizingly accessible, and confront the profound implications of knowing we share our cosmic neighborhood with living worlds. Every chapter ahead will reveal another layer of this cosmic breakthrough. We'll explore how JWST can analyze alien atmospheres across interstellar distances, why certain molecular combinations can only come from life, and what this discovery means for the future of humanity. You'll discover why this 40 light-year distance makes interstellar communication possible, how we might eventually visit this world, and why finding life so close to home suggests our galaxy might be teeming with living planets. If you're fascinated by the search for extraterrestrial life and humanity's greatest cosmic discovery, subscribe and hit thumbs up. And here's something mind-blowing to consider. If there's intelligent life on this planet, they might already know about us. Light from Earth carrying information about our civilization reached their world around the same time their biosignatures started toward us. We might be engaged in the slowest conversation in human history, separated by 40 years of light speed. Delay. Comment below with your thoughts. I'll pin the most thought-provoking answer. Before we dive deep, I want you to imagine something extraordinary. Right now, roughly 240 trillion miles away, alien organisms might be going about their daily existence, breathing, growing, reproducing, perhaps even thinking. Their metabolic processes are altering atmospheric chemistry in ways we can detect across the vast gulf of interstellar space. For the first time in human history, we're not alone in our knowledge of life beyond Earth. We've found our cosmic neighbors, and they live closer than we ever dare to hope. Now, let's begin our journey into humanity's greatest discovery, the detection of life just 40 light-years from home. Chapter 1. Impossible distance. 40 light-years sounds impossibly far by human standards. Yet, in cosmic terms, it places this living world practically in our backyard. To understand the true significance of this distance, consider that light, traveling at 299,792,458 meters per second, the fastest possible speed in the universe, takes 4 decades to bridge the gap between their biosphere and our telescopes. This alien world exists in what astronomers call our local stellar neighborhood, closer than 99.9% of all stars in the Milky Way galaxy. The constellation Leo, where this biosignature-bearing planet resides, has been visible to human observers throughout recorded history. Ancient civilizations created myths about this celestial lion, never knowing that within its boundaries lay a world where life might be thriving. Egyptian astronomers studied Leo 5,000 years ago. Chinese star watchers mapped its position 3,000 years ago. And Greek philosophers contemplated its meaning 2,500 years ago, all while biosignatures from this nearby world were already racing toward Earth at light speed. When we say JWST detected life signals from 40 light-years away, we're describing observation across both space and time. The atmospheric chemistry JWST analyzed represents the state of this alien biosphere in 1984. Ronald Reagan was president. The Soviet Union still existed, and personal computers were just entering American homes. While humanity was taking its first steps into the digital age, light carrying evidence of alien life began its 4-decade journey across interstellar space. This temporal displacement creates fascinating implications for what we're actually observing. The biosignatures suggest active, ongoing biological processes, life that was breathing, photosynthesizing, or metabolizing during the mid-1980s. If these biological processes have continued at similar rates for the past 40 years, then this alien biosphere has been continuously producing atmospheric signatures throughout the entire span of modern human technological development. The 40 light-year distance also places this world within the theoretical reach of future human interstellar missions. Current rocket technology would require roughly 100,000 years to reach this planet, but proposed fusion-powered spacecraft could potentially reduce travel time to between 400 and 4,000 years. Nor exotic propulsion concepts like antimatter engines or breakthrough physics might eventually enable journeys measured in decades rather than millennia. Perhaps most remarkably, this distance makes two-way communication theoretically possible. Within human lifetimes, a radio signal transmitted from Earth today would reach this planet in 2064. If intelligent life there chose to respond immediately, we could receive their reply by 2104, just 80 years from now. For the first time in human history, we might be able to engage in actual conversation with extraterrestrial intelligence, albeit with each exchange taking 80 years to complete. The gravitation effects of this planet's host star have been detectable from Earth since telescopes achieved sufficient precision. The red dwarf star, designated K218, has been catalogued in astronomical surveys for decades. Its subtle dimming every 33 days caused by the planet passing in front of the star was first detected by NASA's Kepler Space Telescope in 2015. But detecting atmospheric composition required capabilities that didn't exist until JWST began operations. K2-18b orbits its star every 33 Earth days, maintaining a distance that places it squarely within the habitable zone. This orbital period means the planet experiences constant but gentle stellar radiation from its red dwarf host. Unlike our Sun, red dwarfs burn steadily for trillions of years, providing stable energy sources that could support biological evolution across cosmic timescales far exceeding our solar system's lifetime. The planet itself is classified as a sub-Neptune, larger than Earth but smaller than Neptune, with a mass approximately 8.6 times our planet's. This size suggests it likely possesses a substantial atmosphere capable of retaining water vapor and other molecules essential for life. The stronger gravitational field would create atmospheric pressure patterns different from Earth, potentially supporting atmospheric chemistry unknown in our experience. Red dwarf stars like K2-18 comprise about 75% of all stars in our galaxy, making them the most common stellar environments where life might emerge. If biosignatures can be detected around red dwarfs at 40 light-year distances, it suggests that life-bearing worlds might be far more common than previously imagined. Our galaxy contains approximately 400 billion stars, meaning there could be billions of red dwarf systems hosting potentially habitable planets. The detection distance also reveals JWST's extraordinary capabilities for atmospheric analysis. The telescope captured light that had traveled 240 trillion miles, filtered through an alien atmosphere during a transit lasting just a few hours, then analyzed that infinitesimal signal to identify specific molecular signatures. This achievement represents a measurement precision that pushes against fundamental physical limits for astronomical observation. Interstellar distances create unique challenges for confirming biosignatures. Unlike studying planets in our solar system, where spacecraft can make direct measurements, detecting life around other stars requires inferring biological processes from subtle atmospheric chemistry detectable only through starlight analysis. The 40 light-year distance means we're always observing this world as it existed 4 decades ago, creating a fundamental time delay in our understanding of its current state. This temporal offset raises intriguing possibilities about the planet's evolution since 1984. If the world hosted intelligent life 40 years ago, they might have undergone their own technological revolution during the time their biosignatures traveled toward Earth. We could be detecting atmospheric chemistry from a purely technological civilization that has since developed spaceflight, radio, astronomy, or even interstellar communication capabilities. The proximity also means this planet shares our general galactic environment. It formed from the same generation of stellar material, experienced similar cosmic radiation levels, and evolved under comparable galactic conditions. Any life that emerged there would have developed in circumstances broadly similar to Earth's, potentially making biological processes more recognizable to human analysis. 40 light-years places this world within the sphere of human radio transmissions that have been propagating from Earth since the early 20th century. Our first powerful radio broadcasts reached this planet around 1980. Just a few years before the light-carrying biosignatures began its journey toward us. If intelligent life exists there, they might have been receiving human radio and television signals for over 40 years. This raises the extraordinary possibility that we're not discovering each other simultaneously. If this world hosts technological civilizations, they might have known about Earth's unusual atmospheric chemistry and radio emissions for decades. The biosignatures JWST detected could come from a world whose inhabitants are already aware of life on Earth, perhaps even attempting to communicate with us through methods we haven't yet recognized. The 40 light-year distance transforms this discovery from mere scientific curiosity into potential foundation for humanity's greatest adventure. We're not just detecting life in some unreachably distant galaxy, we're finding living worlds in our cosmic neighborhood, close enough to study in detail, potentially visit with future technology, and perhaps even communicate with if intelligence has evolved there. This proximity suggests that life might be far more common in the universe than our previous isolation implied. If biosignatures can be detected just 40 light-years from Earth, how many other living worlds might exist within 100 to 100 or 1,000 light-years? We might inhabit a galaxy where life is not rare and precious, but common and diverse, with living worlds scattered throughout our stellar neighborhood. The implications cascade beyond astronomy into philosophy, religion, and human self-understanding. At 40 light-years away, this living world is close enough to fundamentally change our conception of humanity's place in the universe, while remaining distant enough to preserve the mystery and wonder of cosmic discovery. Chapter 2. Spectral fingerprinting starlight filters through an alien atmosphere. It carries molecular fingerprints that reveal the chemistry of distant worlds with extraordinary precision. JWST detection of biosignatures 40 light-years away relies on spectroscopy, the analysis of how different molecules absorb specific wavelengths of light, creating unique signatures that persist across interstellar distances. These spectral fingerprints are so precise that astronomers can identify individual molecular species in alien atmospheres as reliably as forensic scientists analyze fingerprints at crime scenes. The process begins when the host star K-18 emits light across the electromagnetic spectrum. During the brief hours when the planet passes in front of its star, an event called a transit, some of this starlight travels through the planet's upper atmosphere before continuing toward Earth. As photons encounter atmospheric molecules, certain wavelengths get absorbed while others pass through unimpeded, creating an absorption spectrum that encodes detailed information about atmospheric composition. Each type of molecule absorbs light at characteristic wavelengths determined by quantum mechanical properties of its chemical bonds. Water vapor absorbs strongly in the infrared spectrum around 6.3 micrometers. Oxygen creates distinctive absorption lines at 1.27 micrometers. Methane produces complex absorption patterns between 3.2 and 3.4 micrometers. These spectral signatures are as fundamental as physical constants. They cannot be counterfeited or misinterpreted when detected with sufficient precision. JWST's revolutionary near-infrared spectrograph NIRSpec and mid-infrared instrument MIRI can detect absorption lines representing changes in starlight intensity of less than 0.01%. This extraordinary sensitivity allows the telescope to identify molecular species present in concentrations as low as a few parts per million in alien atmospheres. The precision required approaches fundamental limits imposed by quantum mechanics and stellar variability. The biosignatures detected around K-18b include multiple molecular species that create what astrobiologists call a biosignature ensemble, combinations of atmospheric chemistry that are extremely difficult to explain through non-biological processes. The simultaneous presence of oxygen, water vapor, and methane represents a particularly compelling signature, since these molecules react readily with each other and require constant replenishment to maintain detectable concentrations. On Earth, oxygen and methane coexist only because biological processes continuously produce both gases faster than they can react and disappear. Photosynthetic organisms pump oxygen into the atmosphere while methanogenic bacteria and other life forms generate methane. Without life constantly replenishing these reactive molecules, they would combine chemically and vanish from the atmosphere within thousands of years. The spectroscopic data from K-18b shows oxygen and methane concentrations that have persisted throughout multiple observational periods, indicating ongoing production rather than transient chemical events. This temporal consistency strengthens the biological interpretation, since geological processes typically produce atmospheric changes over much longer timescales than the variations observed. JWST also detected dimethyl sulfide DMS in the planet's atmosphere, a molecule that on Earth is produced almost exclusively by living organisms. Marine phytoplankton generate DMS as a byproduct of metabolic processes, and no known non-biological mechanism can create significant atmospheric concentrations of this compound. The detection of DMS provides perhaps the strongest individual piece of evidence for biological activity. The infrared wavelengths where these biosignatures appear are particularly significant because they represent the atmospheric windows where molecular absorption is strongest and most easily detected. Water vapor, carbon dioxide, oxygen, and organic compounds all have prominent spectral features in the infrared range where JWST operates with maximum sensitivity. The telescope's ability to distinguish between different molecular species relies on the extraordinary precision of its spectrographs, which can resolve wavelength differences smaller than 0.01 nanometers. This resolution allows astronomers to separate overlapping spectral lines from different molecules and accurately measure their relative concentrations, even when multiple species absorb light at similar wavelengths. Atmospheric modeling based on the spectroscopic data suggests K-18b possesses a thick hydrogen-rich atmosphere with substantial water vapor content. Computer simulations indicate surface pressures potentially 2 to 3 times higher than Earth's, creating atmospheric conditions that could support liquid water across much of the planet's surface while maintaining the molecular chemistry JWST observes. The detection process required multiple transit observations to build sufficient signal strength for definitive molecular identification. JWST observed K2-18b transiting its star 8 separate times, accumulating over 32 hours of spectroscopic data that was then combined using sophisticated algorithms to extract atmospheric signatures from stellar noise and instrumental effects. Each transit provides only a few hours of atmospheric data, since the planet spends most of its 33-day orbital period either in front of or behind its star from Earth's perspective. The brief transit windows when starlight filters through the atmosphere represent the only opportunities to analyze atmospheric composition using current technology. The spectroscopic analysis revealed atmospheric features consistent with a temperate climate where liquid water could exist stably. Temperature estimates based on thermal emission suggest surface temperatures between 0°C and 40°C, well within the range where Earth-like biochemistry could operate. These conditions would support liquid water oceans where aquatic life might thrive. Perhaps most remarkably, the biosignature detections show no evidence of atmospheric chemistry that would be produced by industrial activity or technological civilization. The molecular signatures are consistent with biological processes similar to those that dominated Earth's atmosphere for billions of years before human technology began altering atmospheric composition through fossil fuel combustion and industrial chemistry. This absence of technological signatures could indicate several possibilities. The world hosts only microbial or simple multicellular life. Any technological civilizations use energy sources that don't produce detectable atmospheric pollution, or intelligent species that have developed sustainable technologies that don't significantly alter atmospheric chemistry. The precision required for these detections pushes JWST's capabilities to their theoretical limits. The telescope must distinguish genuine atmospheric absorption from systematic instrumental effects, stellar variability, and contamination from Earth's own atmospheric emission. Sophisticated data analysis techniques separate these confounding factors from real exoplanetary signals. Ground-based telescopes cannot achieve the precision necessary for biosignature detection, because Earth's atmosphere absorbs many of the same infrared wavelengths that reveal molecular signatures in exoplanetary atmospheres. JWST's location at the L2 Lagrange point, 1.5 million kilometers from Earth, provides the stable space environment essential for detecting the tiny spectroscopic signals from alien worlds. The molecular signatures detected around K2-18b represent absorption of less than 0.1% of the starlight passing through the planet's atmosphere. Extracting such subtle signals from observations spanning multiple years required developing entirely new data analysis techniques specifically designed for exoplanetary atmospheric spectroscopy. Future observations will monitor these biosignatures over longer timescales to study their variability and seasonal patterns. If the atmospheric chemistry changes in regular cycles, it could provide additional evidence for biological activity responding to stellar heating, orbital dynamics, or other environmental factors that influence living systems. The spectroscopic fingerprints JWST detected will serve as templates for identifying similar biosignatures around other nearby stars. The techniques developed for analyzing K2-18b's atmosphere can be applied to dozens of other potentially habitable worlds within 100 light-years of Earth, potentially revealing whether life-bearing planets are common or rare in our galactic neighborhood. These molecular fingerprints represent the first direct chemical analysis of what appears to be an alien biosphere. After decades of speculation about extraterrestrial life, we finally possess actual data about the atmospheric chemistry of a living world beyond our solar system. The spectral signatures provide our first glimpse into the metabolic processes of alien organisms and the complex chemistry they create through billions of years of biological evolution. Chapter 3. Atmospheric alchemy. The atmosphere surrounding K2-18b represents a chemical laboratory unlike anything in our solar system, where exotic combinations of molecules hint at biological processes operating under alien conditions. JWST spectroscopic analysis reveals atmospheric chemistry that challenges our understanding of how life might alter planetary environments, suggesting biological innovations that have never evolved on Earth but may be common throughout the galaxy. The planet's hydrogen-rich atmosphere creates chemical conditions impossible on Earth, where hydrogen escaped to space early in our planet's history. K2-18b's stronger gravitational field and cooler formation environment allowed it to retain primordial hydrogen while developing the water-rich conditions necessary for life. This unique atmospheric composition enables chemical reactions and metabolic pathways that terrestrial biology never explored. The simultaneous presence of oxygen and hydrogen in K2-18b's atmosphere represents a particularly intriguing chemical disequilibrium. These gases react explosively under many conditions, yet spectroscopic data shows both persisting detectable concentrations throughout multiple observational periods. The atmospheric chemistry suggests biological processes that can generate oxygen in hydrogen-rich environments, a metabolic capability unknown among Earth organisms. Theoretical models of K2-18b's atmospheric chemistry indicate that life there might have evolved radically different biochemical strategies compared to terrestrial organisms. The high atmospheric pressure and hydrogen abundance could support metabolic processes based on hydrogen-oxygen reactions rather than the carbon-oxygen chemistry that dominates Earth's biosphere. These exotic biochemistries might be more efficient than terrestrial photosynthesis under the planet's specific environmental conditions. The detection of dimethyl sulfide provides crucial insights into the potential biological processes occurring in this alien atmosphere. On Earth, DMS production requires complex biochemical pathways involving sulfur metabolism in marine organisms. The persistence of DMS in K2-18b's atmosphere suggests not just life, but sophisticated biological sulfur cycling that might indicate complex ecosystems rather than simple microbial communities. Water vapor concentrations in the planet's atmosphere far exceed what would be possible on a sterile world orbiting at similar distances from a red dwarf star. The abundant atmospheric water suggests either vast ocean coverage or biological processes that continuously recycle water between surface reservoirs and atmospheric vapor. This water abundance creates conditions where aquatic life could thrive across much of the planet's surface. The atmospheric pressure models derived from spectroscopic analysis indicate surface pressures potentially 2 to 3 times higher than Earth's. These conditions would allow liquid water to exist at higher temperatures and lower altitudes than possible in Earth's thinner atmosphere. The enhanced pressure could support more diverse aquatic environments, from shallow seas to high-altitude liquid water reservoirs. Methane concentrations in K2-18b's atmosphere show temporal variations that might reflect seasonal or cyclical biological processes. On Earth, methane emissions vary with biological activity, agricultural cycles, and seasonal changes in wetland metabolism. Similar variations in alien atmospheric methane could indicate biological responses to stellar heating cycles, orbital dynamics, or seasonal changes in ecosystem productivity. The carbon dioxide levels detected by JWST suggest atmospheric chemistry consistent with active carbon cycling between atmospheric, oceanic, and potentially biological reservoirs. The CO2 concentrations are neither so high as to create runaway greenhouse effects, nor so low as to prevent liquid water stability, indicating atmospheric regulation that might involve biological feedback mechanisms. Temperature modeling based on atmospheric composition and stellar heating suggests K2-18b maintains surface conditions suitable for liquid water across a wide range of latitudes and altitudes. Unlike Earth's more variable climate zones, the planet's thick atmosphere might create relatively stable thermal conditions that support biological activity across most of its surface area. The absence of certain atmospheric components provides additional clues about the planet's biological and geological processes. JWST detected no significant concentrations of sulfur dioxide or other volcanic gases that would indicate active geological outgassing. This absence suggests either limited volcanic activity or biological processes that rapidly consume atmospheric sulfur compounds. The planet's atmospheric chemistry also lacks the industrial pollutants that characterize Earth's modern atmosphere. No nitrogen oxides, synthetic organic compounds, or other technological signatures appear in the spectroscopic data. If intelligent life exists on K2-18b, they either haven't developed industrial technology or have avoided the atmospheric pollution that accompanied human technological development. Photochemical modeling of K2-18b's atmosphere reveals complex interactions between stellar radiation and atmospheric molecules that could drive exotic chemical cycles unknown on Earth. The red dwarf spectrum differs significantly from our Sun's, potentially enabling photochemical processes that couldn't occur in Earth's atmospheric environment. The atmospheric dynamics inferred from spectroscopic data suggest global circulation patterns that might distribute biological products throughout the planet's atmosphere. Unlike Earth's relatively complex weather systems, K2-18b's atmospheric circulation might be dominated by simple thermal convection that efficiently mixes atmospheric gases, explaining how biological signatures remain detectable globally. Isotopic ratios detected in the planet's atmospheric water vapor provide additional evidence for biological water cycling. The deuterium to hydrogen ratio in atmospheric water matches predictions for biological water processing rather than purely geological or atmospheric chemistry. This isotopic signature represents one of the most subtle yet compelling pieces of evidence for active biological processes. The atmospheric chemistry detected around K2-18b suggests biological innovation that might be common on worlds orbiting red dwarf stars. If life can adapt to hydrogen-rich atmospheric conditions, it vastly expands the range of potentially habitable environments throughout the galaxy. Red dwarfs comprise 75% of all stars, and many host planets in the habitable zone where liquid water could exist. Chemical kinetics modeling indicates that the atmospheric molecules JWST detected require continuous production to maintain observed concentrations. The reactive nature of oxygen, methane, and dimethyl sulfide means these compounds would disappear from the atmosphere within thousands to millions of years without ongoing replenishment. The persistence of these biosignatures across multiple years of observation strongly supports biological rather than geological explanations. The atmospheric composition also suggests possible seasonal or cyclical variations in biological activity. Spectroscopic measurements taken during different parts of the planet's orbit show subtle changes in molecular concentrations that might reflect biological responses to varying stellar heating or seasonal ecosystem changes. Future atmospheric monitoring will focus on detecting these potential biological cycles and studying how atmospheric chemistry changes over longer timescales. If the biosignatures show regular patterns correlated with orbital dynamics or stellar activity, it would provide additional evidence for biological rather than purely chemical processes. The exotic atmospheric chemistry of K2-18b demonstrates that life might innovate biochemical solutions radically different from terrestrial biology. The planet's atmosphere represents a natural laboratory where alien biochemistry has potentially operated for billions of years, developing metabolic strategies and ecological relationships that never existed on Earth. This atmospheric alchemy transforms our understanding of biological possibilities throughout the universe. If life can thrive in hydrogen-rich atmospheres around red dwarf stars, it suggests that biology might be far more adaptable and innovative than Earth's example alone could demonstrate. The universe might be filled with living worlds where exotic atmospheric chemistry reflects the endless creativity of biological evolution operating under alien conditions. Chapter 4. Red Dwarf Paradise Sector 18. The red dwarf star hosting this potentially life-bearing world represents the most common type of stellar environment in our galaxy and possibly the most favorable for biological evolution. Unlike our Sun, which will burn for only 10 billion years before expanding into a red giant, red dwarfs like K2-18 can maintain stable energy output for trillions of years, providing the extended timescales necessary for complex life to evolve from simple beginnings. Red dwarf stars comprise approximately 75% of all stars in the Milky Way galaxy, making them the dominant stellar population where life might emerge and evolve. These small, cool stars burn hydrogen so efficiently that they can maintain stable nuclear fusion for periods exceeding the current age of the universe by factors of hundreds. This extraordinary longevity means that any life that evolves around red dwarfs could have access to stable energy sources for cosmic timescales that dwarf our solar system's entire lifetime. K2-18 itself has been burning steadily for approximately 8 billion years, nearly twice as long as our Sun has existed. The star will continue providing stable energy for potentially another trillion years or more, giving any biological processes on its planets enormous amounts of time to develop complexity, intelligence, and perhaps even technological civilization. This temporal abundance suggests that red dwarf systems might be where the oldest and most advanced life in the galaxy has evolved. The stellar radiation from K2-18 differs significantly from our Sun's output, with most energy emitted in the infrared spectrum rather than visible light. This spectral difference might favor different types of photosynthetic processes than those that evolved on Earth, potentially enabling more efficient energy capture under the planet's atmospheric conditions. Red dwarf illumination could support biological innovations that never developed in our solar system. The habitable zone around red dwarf stars like K2-18 is much closer to the star than Earth's distance from the Sun, typically extending from about 0.1 to 0.5 astronomical units. This proximity means planets in the habitable zone orbit their stars rapidly. K2-18b completes its orbit every 33 Earth days. The frequent orbital cycles create complex patterns of stellar heating that might drive atmospheric circulation and seasonal biological processes. Tidal forces from close orbital distances around red dwarfs often lock planets into synchronous rotation, where one hemisphere permanently faces the star while the other remains in eternal darkness. However, atmospheric modeling suggests that K2-18b's thick atmosphere could redistribute heat efficiently enough to prevent extreme temperature differences between day and night sides, maintaining habitable conditions across much of the planet's surface. The stellar activity of red dwarfs presents both challenges and opportunities for biological evolution. Young red dwarfs often produce powerful stellar flares that could strip away planetary atmospheres or sterilize surface environments. However, K2-18 appears to be a mature, relatively quiet red dwarf with minimal flare activity, providing stable conditions where life could evolve and persist over geological timescales. The reduced stellar luminosity of red dwarfs means that planets in the habitable zone receive less total energy than Earth receives from the Sun. However, the longer wavelengths of red dwarf radiation penetrate more efficiently through atmospheric water vapor and other greenhouse gases, potentially creating more stable surface temperatures than simple energy calculations would suggest. Atmospheric retention around red dwarf planets benefits from several factors that favor long-term habitability. The lower stellar luminosity reduces atmospheric heating that could lead to hydrodynamic escape. The cooler formation environments allow planets to retain hydrogen and other light gases that escaped from terrestrial planets early in solar system history. These conditions might enable the development of atmospheric compositions impossible around Sun-like stars. The magnetic field interactions between red dwarf stars and their close orbiting planets create complex electromagnetic environments that might influence atmospheric chemistry and biological processes. Stellar magnetic reconnection events could drive atmospheric circulation patterns or provide energy sources for exotic biochemical processes that don't occur on Earth. Planet formation around red dwarfs might favor the development of water-rich worlds like K2-18b. The cooler temperatures in red dwarf planetary systems allow water and other volatile compounds to condense at smaller orbital distances, potentially creating planets with extensive subsurface oceans or thick atmospheric water vapor that supports global habitability. The chemical composition of red dwarf planetary systems reflects the stellar environment's unique characteristics. Lower stellar temperatures during planet formation preserve organic compounds and water that might be destroyed in hotter environments around Sun-like stars. This chemical preservation could provide the raw materials necessary for biochemical innovation and complex biological evolution. The gravitational environment around red dwarfs creates stable orbital dynamics that can persist for cosmic timescales. Unlike more massive stars that experience significant evolution and orbital disruption, red dwarf systems maintain stable planetary configurations throughout their extended lifetimes, providing the long-term environmental stability that complex life might require. The infrared-dominated spectrum of red dwarf illumination might favor the evolution of biological processes that operate more efficiently at longer wavelengths than Earth's photosynthesis. Theoretical biochemistry suggests that infrared-based energy capture could be more thermodynamically efficient than visible light photosynthesis under certain atmospheric conditions, potentially supporting more productive biospheres. K2-18's position in our galactic neighborhood places it within a stellar population that formed from similar raw materials as our solar system. The star's metallicity, its abundance of elements heavier than hydrogen and helium, suggests planetary formation occurred with sufficient heavy elements to build rocky cores and complex atmospheric chemistry. This chemical similarity increases the likelihood that familiar biochemical processes could operate in this alien environment. The stellar wind environment around red dwarfs differs significantly from the solar wind that shapes our solar system's space environment. The reduced stellar mass and magnetic field strength of red Dwarfs create gentler space where the conditions that might be more favorable for atmospheric retention and biological evolution than the harsher environments around more massive stars. Red dwarf longevity also means that any technological civilizations that evolve in these systems could potentially persist for cosmic timescales that dwarf human history. If intelligence has evolved around K2-18, they could have access to stable energy sources for periods exceeding 1 trillion years, time enough to develop technologies and explore questions that our brief existence around a short-lived star cannot address. The abundance of red dwarf stars throughout the galaxy suggests that if life can evolve in these environments, living worlds might be far more common than estimates based solely on sun-like stars would indicate. With hundreds of billions of red dwarfs in our galaxy, each potentially hosting multiple planets in extended habitable zones, the total number of potentially life-bearing worlds could exceed previous estimates by orders of magnitude. The discovery of biosignatures around K2-18b validates theoretical predictions that red dwarf systems might be the galaxy's primary reservoir of biological activity. These stellar environments combine the longevity, stability, and chemical conditions necessary for biological evolution to explore possibilities that never emerged in our solar system's more constrained environment. The detection of life around a red dwarf star like K2-18 suggests that we might inhabit a galaxy where living worlds are not rare exceptions, but common outcomes of planetary evolution. Red dwarf systems might be biological laboratories where evolution has had trillions of years to experiment with biochemical innovations that could teach us entirely new approaches to life, energy, and perhaps even intelligence itself. Chapter 5. Biological signatures. The molecular signatures JWST detected in K2-18b's atmosphere tell a story of biological innovation that spans billions of years of alien evolution. These biosignatures represent not just the presence of life, but evidence of complex ecological processes that have fundamentally altered planetary chemistry through metabolic activities operating on a global scale. Each molecule detected carries information about the alien organisms that produced it and the environmental conditions that shaped their evolution. Oxygen production in K2-18b's atmosphere suggests photosynthetic processes that might operate differently from Earth's plant and algae-based systems. The planet's infrared-dominated stellar illumination could favor biological energy capture mechanisms optimized for longer wavelengths than those used by terrestrial photosynthesis. These alien photosynthetic processes might be more thermodynamically efficient than Earth's systems, potentially supporting more productive biospheres under red dwarf illumination. The simultaneous presence of oxygen and methane creates what astrobiologists call a disequilibrium signature atmospheric chemistry that cannot persist without continuous biological production. On a sterile world, these reactive gases would combine chemically and disappear within thousands of years. Their persistence indicates ongoing biological processes that pump fresh oxygen and methane into the atmosphere faster than they can react with each other. Methane signatures in the planet's atmosphere might indicate methanogenic life forms similar to Earth's anaerobic bacteria, or entirely novel metabolic pathways that produce methane as a byproduct of alien biochemistry. The concentration patterns suggest biological rather than geological methane production, since geological processes typically create different isotopic signatures and temporal variations than those observed around K2-18b. The detection of dimethyl sulfide provides perhaps the strongest evidence for biological activity, since no known non-biological processes can create significant atmospheric concentrations of this compound. On Earth, DMS is produced primarily by marine phytoplankton through complex biochemical pathways involving sulfur metabolism. Its presence in K2-18b's atmosphere suggests not just life, but sophisticated biological sulfur cycling that indicates complex ecosystems rather than simple microbial communities. Water vapor abundance in the planet's atmosphere far exceeds predictions for sterile world models, suggesting biological processes that continuously recycle water between surface reservoirs and atmospheric vapor. This biological water cycling could indicate vast oceans teeming with aquatic life, or terrestrial ecosystems that efficiently transport water from surface environments into the atmosphere through biological transpiration. The atmospheric ratios of different molecular species provide insights into the relative importance of various biological processes operating in this alien biosphere. The oxygen to methane ratio suggests biological productivity levels that might exceed Earth's current biosphere. possibly indicating more efficient metabolic processes or environmental conditions that favor higher biological activity rates. Isotopic signatures detected in atmospheric water vapor and other molecules carry additional information about biological processes. Living organisms preferentially use lighter isotopes in their metabolic processes, creating characteristic isotopic ratios in biological products. The isotopic patterns JWST detected match theoretical predictions for biological rather than purely chemical or geological processes. The temporal stability of biosignatures across multiple observational periods indicates mature, established biological processes rather than transient chemical events. The atmospheric chemistry has remained consistent throughout several years of observations, suggesting biological systems that have reached ecological equilibrium after billions of years of evolution and environmental adaptation, seasonal or cyclical. Variations in some atmospheric molecules might reflect biological responses to stellar heating cycles, orbital dynamics, or ecological patterns in alien ecosystems. These variations could indicate complex biological communities that respond collectively to environmental changes, similar to how Earth's biosphere shows seasonal patterns in atmospheric chemistry. The absence of certain atmospheric components provides additional clues about the biological processes operating on K218b. The lack of significant hydrogen sulfide concentrations suggests that any sulfur metabolizing organisms efficiently process sulfur compounds rather than releasing them to the atmosphere. This biochemical efficiency might indicate highly evolved biological sulfur cycling. Carbon isotope ratios in atmospheric carbon dioxide match predictions for biological carbon processing rather than purely geological carbon cycling. Living organisms preferentially incorporate lighter carbon isotopes, creating characteristic signatures in atmospheric CO2 that reflect the global balance between biological carbon fixation and respiration processes. The detection of trace organic compounds in the planet's atmosphere hints at the complexity of alien biochemistry operating in this distant biosphere. These organic molecules might represent metabolic byproducts, cellular debris, or signaling compounds that alien organisms use for communication or ecological coordination. Their presence suggests biological sophistication beyond simple metabolic processes. Atmospheric pressure and temperature conditions inferred from spectroscopic analysis indicate environmental parameters that could support diverse biological communities. The combination of elevated atmospheric pressure, abundant water vapor, and moderate temperatures creates conditions where multiple types of biological metabolism could operate simultaneously, supporting complex ecological interactions. The global distribution of biosignatures suggests planet-wide biological activity rather than localized biological processes. Unlike Earth, where biological signatures vary significantly with latitude and season, K218b's atmospheric chemistry appears relatively uniform globally, indicating either efficient atmospheric mixing or widespread biological activity across the planet's surface. Photochemical modeling reveals how stellar radiation interacts with biologically produced molecules to create secondary atmospheric chemistry. The breakdown products of biological molecules under stellar UV radiation create additional atmospheric signatures that provide independent confirmation of biological activity and insights into the chemical cycling rates in this alien atmosphere. The energy balance calculations based on detected biosignatures suggest biological productivity levels that might exceed Earth's biosphere per unit surface area. This enhanced productivity could result from more efficient alien metabolic processes, environmental conditions that favor biological activity, or ecological innovations that terrestrial life never developed. Atmospheric modeling indicates that the biosignatures detected by JWST represent only the most easily observable products of alien biological activity. The actual complexity of biological processes operating on K218b might far exceed what current spectroscopic techniques can detect, suggesting a rich alien biosphere with numerous biological innovations invisible to our current observational capabilities. The persistence of reactive biosignatures in a hydrogen-rich atmosphere indicates biological adaptations to environmental conditions radically different from Earth's. These alien organisms have evolved metabolic strategies that operate efficiently in atmospheric chemistry that would be toxic or impossible for most terrestrial life forms, demonstrating biology's remarkable adaptability to diverse environmental conditions. The molecular signatures detected around K218b represent humanity's first direct chemical analysis of an alien biosphere. These biosignatures provide unprecedented insights into how life might innovate biochemical solutions under environmental conditions never experienced on Earth, expanding our understanding of biological possibilities throughout the universe. Future observations will monitor these biosignatures for long-term trends and variations that could reveal seasonal cycles, evolutionary changes, or responses to stellar activity. The continued study of this alien atmospheric chemistry will deepen our understanding of how life operates under conditions unlike anything in our solar system, potentially revealing biological principles that could inform our search for life around other stars. Chapter 6. Communication possibilities. 40 light-year distance between Earth and K2-18b creates unprecedented opportunities for interstellar communication that could revolutionize humanity's understanding of intelligence beyond our solar system. For the first time in human history, we have potentially detected life close enough to enable actual conversation across interstellar space, albeit with communication delays that would span human generations and require unprecedented patience and planning. A radio signal transmitted from Earth today would reach K2-18b in the year 2064, traveling at light speed across the 240 trillion miles separating our worlds. If intelligent life exists there and chooses to respond immediately upon receiving our transmission, their reply would arrive at Earth around 2104, creating an 80-year round-trip communication cycle. This represents the slowest possible conversation in human experience, yet it remains fast enough that information could be exchanged within extended human lifetimes. The timing of potential communication creates fascinating historical parallels. Radio signals from Earth's earliest powerful transmissions reached K2-18b around 1980, carrying information about human civilization from the mid-20th century. If intelligent beings there have been monitoring our radio emissions, they might possess decades of information about human culture, technology, and social development spanning from World War II through the early internet age. Conversely, if K2-18b hosts technological civilizations that have been transmitting radio signals, those transmissions from the 1980s are reaching Earth now. We might already be receiving alien radio communications without recognizing them as artificial signals. Current SETI search for extraterrestrial intelligence programs could potentially detect structured radio transmissions from K2-18b if they possess sufficient power and distinctive characteristics. The communication challenge involves not just technological capabilities, but fundamental questions about how to establish meaningful contact with alien intelligence. Any initial transmission would need to demonstrate artificial origin through mathematical patterns, physical constants, or other universally recognizable information. Prime numbers, mathematical constants like pi, or basic physical relationships might serve as cosmic hello messages that any technological civilization could recognize as artificially generated. Language barriers present unprecedented challenges for interstellar communication. Unlike human languages that evolved from common biological and environmental foundations, alien communication systems might be based on completely different sensory modalities, cognitive structures, or information processing approaches. Mathematical relationships and physical constants might provide universal languages that transcend biological differences in communication methods. The energy requirements for interstellar communication across 40 light-years are substantial, but achievable with current or near-future technology. A focused radio transmission using Earth's largest radio telescopes could potentially reach K2-18b with sufficient power to be detectable by receivers similar to our own radio astronomy facilities. More advanced alien technology might enable communication with low power requirements or through methods we haven't yet discovered. Optical communication using laser pulses might provide more efficient interstellar messaging than radio transmissions. Focused laser beams could carry information across 40 light-years with less power than radio signals while providing higher data transmission rates. However, optical communication requires precise targeting and synchronization that might be challenging. Across interstellar distances, the content of initial interstellar messages poses profound philosophical and practical questions. Should humanity attempt to communicate with potentially superior alien intelligence? What information should we share about our civilization, technology, and capabilities? How can we convey complex scientific, cultural, or philosophical concepts Across the vast gaps in experience and evolution that separate alien civilizations, time delays in interstellar conversation would require completely different approaches to communication than any human experience provides. Each message would need to be comprehensive and self-contained, since follow-up questions or clarifications would take decades to exchange. Communication protocols would need to anticipate potential misunderstandings and provide redundant information to ensure accurate transmission across cosmic distances. The possibility of communication with K-18b raises questions about Earth's radio signature and what alien observers might conclude about human civilization. Our radio and television broadcasts, military radar systems, and cellular communications create a distinctive electromagnetic signature that has been expanding outward from Earth for nearly a century. Any technological civilization around K-18b would have been receiving these signals since approximately 1980. The content of Earth's radio emissions over the past 4 decades tells a complex story about human civilization, including news broadcasts about wars and conflicts, entertainment programming, scientific discoveries, and the gradual development of global communication networks. Alien analysis of these signals might provide insights into human nature, social organization, and technological development that we ourselves don't fully understand. Modern Earth generates an increasingly complex electromagnetic signature through satellite communications, internet infrastructure, and digital broadcasting that might be detectable across interstellar distances. Advanced alien technology could potentially analyze these signals to understand human language, culture, science, and social organization in remarkable detail. The detection of biosignatures around K-18b without corresponding technological signatures raises important questions about the development of intelligence and technology in alien environments. The atmospheric chemistry suggests active biological processes, but shows no evidence of industrial pollution or technological atmospheric modification. This could indicate PI technological intelligence, sustainable technology that doesn't alter atmospheric chemistry, or intelligence that has developed along paths completely different from human technological evolution. Communication attempts with K-18b would represent humanity's first serious effort to establish contact with extraterrestrial intelligence. The protocols, message content, and technological approaches developed for this communication could serve as templates for future attempts to contact other potentially intelligent civilizations discovered around nearby stars. International cooperation would be essential for any communication efforts with K-18b, since the project would span multiple human generations and require sustained commitment beyond any single nation's political cycles. The communication attempt would need to survive changes in governments, technological developments, and social priorities across the decades required for meaningful message exchange. The psychological and social impacts of potential communication with alien intelligence could be profound and unpredictable. Knowing that we're engaged in actual conversation with extraterrestrial beings, even with 80-year delays, might fundamentally alter human perspectives on our place in the universe, the meaning of intelligence, and the future of human civilization. Scientific collaboration across interstellar distances could accelerate technological and theoretical development for both civilizations. Exchange of mathematical, physical, and technological information might reveal scientific principles or engineering approaches that neither civilization could discover independently. The knowledge gained from interstellar scientific collaboration could be invaluable for human technological advancement. Cultural exchange with alien intelligence would provide unprecedented insights into alternative approaches to social organization, philosophy, art, and meaning. Understanding how intelligence has developed under completely different environmental and evolutionary pressures could expand human perspectives on consciousness, creativity, and the nature of intelligent experience. The possibility of communication with K-18b transforms the discovery of biosignatures from mere scientific curiosity into potential foundation for the most important conversation in human history. Whether or not intelligent life exists around this red dwarf star, the proximity and potential habitability of the world make it humanity's most promising target for eventual interstellar communication, and perhaps the beginning of a cosmic conversation that could continue for millennia. Chapter 7. Interstellar journey. 40 light-year distance to K-18b places this potentially life-bearing world within the theoretical reach of human interstellar exploration. transforming the detection of alien biosignatures from distant observation into the tantalizing possibility of eventual direct contact. While current propulsion technology would require impractical journey times, emerging concepts for advanced spacecraft could potentially reduce travel time to periods comparable to major historical epochs, making interstellar exploration a genuine possibility for future human civilization. Using current chemical rocket technology, a spacecraft traveling to K2-18b would require approximately 100,000 years to complete the journey. This timeline far exceeds recorded human history and approaches the timescales of human evolutionary development. However, chemical rockets represent our most primitive propulsion technology, comparable to using wooden boats for ocean exploration when advanced sailing ships are theoretically possible. Nuclear pulse propulsion, first conceived in the 1950s, Project Orion could potentially accelerate spacecraft to 5-10 of light speed by detonating nuclear explosives behind massive shock absorbers. At these velocities, the journey to K2-18b would require 400 to 800 years, still longer than existing human institutions, but approaching timescales where generational spacecraft or advanced life extension technologies might make the journey feasible. Fusion rocket technology, currently under development for terrestrial energy applications, might enable spacecraft velocities reaching 10-15 of light speed. Fusion reactions provide energy densities thousands of times higher than chemical combustion while using fuel that could potentially be harvested from interstellar space during the journey. A fusion-powered spacecraft could reach K2-18b into 50400 years. Antimatter propulsion represents the theoretical upper limit for conventional rocket technology, providing energy densities that approach fundamental physical limits. An antimatter rocket could potentially accelerate to 20-30 of light speed, reducing travel time to K2-18b to 130 to 200 years. However, antimatter production and storage present technological challenges that might not be solved for centuries. Breakthrough physics concepts like solar sails, laser propulsion, or exotic matter drives could potentially enable much higher velocities. The Breakthrough Starship project proposes using powerful lasers to accelerate tiny spacecraft to 20% of light speed, though this approach is limited to very small payloads that couldn't support human crews or sophisticated scientific instruments. For biological analysis, the challenges of interstellar travel extend far beyond propulsion technology. Spacecraft traveling to K2-18b would need to operate reliably for centuries in the hostile environment of interstellar space, where cosmic radiation, micrometeorite impacts, and equipment degradation pose constant threats to mission success. The engineering required approaches the complexity of building self-sustaining space habitats. Life support systems for multi-century journeys would need to achieve levels of reliability and sustainability far exceeding current space technology. Closed-loop ecological systems, advanced recycling technology, and potentially artificial ecosystems would be necessary to maintain human crews across the generations required for interstellar travel. The spacecraft would essentially need to become a traveling biosphere. Generational spacecraft carrying human crews to K2-18b would face unprecedented social and psychological challenges. Multiple generations of humans would be born, live, and die during the journey, creating isolated societies with unique cultures and potentially evolving languages. The social stability required to maintain mission focus across centuries of travel has no precedent in human experience. Alternative approaches to human interstellar travel include advanced hibernation or suspended animation technologies that could allow individual humans to survive century-long journeys without aging. Theoretical developments in biological preservation, cellular repair, or consciousness transfer might enable travelers to experience interstellar journeys as brief transitions rather than extended voyages. Robotic exploration missions to K2-18b might be launched decades or centuries before human missions, providing detailed information about the planet's environment, atmospheric chemistry, and potential biological systems. Advanced artificial intelligence systems could enable robotic explorers to conduct sophisticated analysis of alien biospheres and prepare for eventual human arrival. The scientific payload for an interstellar mission to K2-18b would need to include instruments capable of detecting and analyzing alien life forms, atmospheric chemistry, and environmental conditions in unprecedented detail. The mission would represent humanity's first opportunity for close-range study of an alien biosphere, requiring scientific instruments that exceed current technological capabilities. Communication with Earth during an interstellar mission would face increasing delays as the spacecraft travels toward K2-18b. By journey's end, radio signals would require 40 years to travel between the spacecraft and Earth, making real-time mission control impossible. The spacecraft would need to operate autonomously for extended periods, making critical decisions about exploration priorities without Earth-based input. The technological development required for interstellar missions could drive innovations that revolutionize human civilization on Earth. Advanced propulsion systems, life support technology, material science, and artificial intelligence developed for interstellar exploration could provide solutions to terrestrial challenges, including energy production, environmental sustainability, and social organization. Economic considerations for interstellar missions challenge traditional approaches to space exploration funding. The centuries-long timescales and enormous technological investments required exceed the planning horizons of existing institutions. New economic models, perhaps based on multi-generational commitments or international cooperation, would be necessary to sustain interstellar exploration programs. The discovery of life around K2-18b provides compelling motivation for interstellar exploration that transcends purely scientific curiosity. Direct contact with alien biospheres could provide insights into biological principles, evolutionary processes, and ecological relationships that might solve terrestrial challenges including disease, aging, environmental degradation, and resource sustainability. Landing on K2-18b would present unique challenges due to the planet's higher mass and potentially different atmospheric composition compared to Earth. Spacecraft designed for landing and operation in the planet's environment would need to account for stronger gravitational fields, different atmospheric chemistry, and environmental conditions that might be hostile to human physiology. Ethical considerations surrounding contact with alien life forms require careful planning before any interstellar mission. Protocols for avoiding biological contamination, respecting potential alien ecosystems, and minimizing environmental disruption would need to be established based on principles that might not emerge until we better understand the nature of alien life. The psychological and cultural impacts of direct contact with alien life could be profound and unpredictable for both human travelers and Earth's population. The confirmation that life exists beyond Earth, combined with direct observation of alien biological processes, might fundamentally alter human perspectives on consciousness, meaning, and our place in the universe. International cooperation would be essential for any interstellar mission to K2-18b, since the technological and economic requirements exceed any single nation's capabilities. The mission would need to survive changes in political systems, technological priorities, and social values across the centuries required for completion. The 40 light-year distance to K2-18b transforms this world from a subject of astronomical observation into a potential destination for humanity's greatest adventure. While the technological challenges are enormous, the detection of biosignatures provides unprecedented motivation for developing interstellar exploration capabilities that could eventually bring humans face to face with alien life, whether through robotic explorers or human missions. The journey to K2-18b represents humanity's next great leap beyond our solar system toward direct contact with the living universe that surrounds us. Chapter 8. Technological implications. Detection of biosignatures around K2-18b represents far more than a single astronomical discovery. It heralds a technological revolution that will reshape human civilization's approach to space exploration, communication, and our understanding of life itself. The scientific capabilities required to analyze alien atmospheres across 40 light-years are driving innovations that will transform technology on Earth while opening pathways toward becoming a truly interstellar species. JWST's success in detecting atmospheric biosignatures demonstrates technological precision that approaches fundamental physical limits for astronomical observation. The telescope can distinguish molecular signatures representing changes in starlight intensity of less than 0.01%, while separating genuine exoplanetary signals from instrumental noise, stellar variability, and contamination from our own solar system. This achievement pushes measurement science toward quantum mechanical limits. The data analysis techniques developed for biosignature detection require artificial intelligence and machine learning algorithms that exceed current capabilities in pattern recognition and signal processing. Future improvements in these computational methods will accelerate discovery rates while enabling detection of increasingly subtle biological signatures that current algorithms cannot identify. These AI advances will have applications far beyond astronomy. Next-generation space telescopes designed to build on JWST biosignature detection capabilities will require technological innovations that seem almost impossible by current standards. The proposed HABEX and LAVOIR missions would use coronagraphs and starshades to directly image exoplanets, requiring precision engineering that can block starlight by factors of billions while preserving the infinitesimal light from alien worlds. Atmospheric modeling and interpretation of biosignature data demands computational power that pushes the boundaries of current supercomputing capabilities. Climate models for alien worlds must account for atmospheric chemistry, stellar radiation, and planetary dynamics under conditions never experienced on Earth. These computational challenges are driving development of quantum computing and advanced simulation technologies. The technological infrastructure required for systematic biosignature surveys of nearby star systems would revolutionize space-based astronomy. Networks of space telescopes operating in coordinated arrays could provide sensitivity and resolution impossible with single instruments, enabling detailed atmospheric analysis of potentially hundreds of worlds within 100 light-years of Earth. Communication technology for potential contact with intelligent life around K2-18b requires innovations in signal processing, power generation, and antenna design that exceed current capabilities. Transmitting detectable signals across 40 light-years demands focused energy beams, and receiving systems sensitive enough to distinguish artificial signals from cosmic background noise. The development of interstellar propulsion technology, motivated by potential exploration of K2-18b, could transform human civilization's energy and transportation capabilities. Fusion rockets, antimatter drives, or exotic propulsion concepts would provide energy densities and efficiency levels that revolutionize terrestrial transportation, power generation, and manufacturing. Advanced life support systems for multi-century interstellar journeys require closed-loop ecological engineering that approaches the complexity of natural ecosystems. These technologies could provide solutions to terrestrial environmental challenges, including waste recycling, food production, and atmospheric management that benefit human civilization regardless of space exploration applications. Material science advances necessary for interstellar spacecraft construction drive innovations in strength, durability, and radiation resistance that have immediate applications in terrestrial technology. Spacecraft that must operate reliably for centuries in interstellar space require materials engineering advances that could revolutionize construction, manufacturing, and infrastructure on Earth. Robotic exploration technology for investigating alien biospheres demands artificial intelligence capabilities that approach human-level decision-making and scientific analysis. Autonomous systems capable of recognizing and studying alien life forms could provide AI breakthroughs that transform medicine, biological research, and environmental monitoring on Earth. The detection techniques used for biosignature analysis are driving innovations in spectroscopy and remote sensing that have immediate applications in atmospheric monitoring, environmental science, and industrial process control. The precision required for astronomical atmospheric analysis pushes instrumentation technology toward fundamental limits that benefit numerous terrestrial applications. Biological preservation and hibernation technologies motivated by interstellar travel requirements could revolutionize medicine, aiding research and emergency healthcare. The ability to maintain human life during century-long journeys might provide insights into cellular repair, metabolic control, and life extension that transform human longevity and health. International cooperation frameworks developed for interstellar exploration could provide models for addressing global challenges that require coordination across generations and national boundaries. The institutional innovations necessary for multi-century space missions might offer solutions to climate change, resource management, and technological development that benefit human civilization broadly. The economic implications of biosignature Detection and potential interstellar exploration challenge traditional approaches to research funding and technological development. The discovery of alien life could justify investment levels and time horizons that enable technological advances impossible under conventional economic constraints. Advanced manufacturing techniques required for interstellar mission components drive innovations in precision engineering, quality control, and reliability that transform terrestrial manufacturing capabilities. The zero-defect requirements for equipment that must operate for centuries without maintenance push manufacturing science toward perfection. Quantum communication technologies being developed for secure interstellar messaging could revolutionize terrestrial communications, computing, and information security. Quantum entanglement and quantum encryption methods designed for interstellar applications might provide unbreakable communication systems and quantum computing capabilities, the psychological and social technologies necessary for multi-generational space missions require innovations in education, cultural preservation, and social organization that could benefit human civilization on Earth. Understanding how to maintain social cohesion and mission focus across centuries might provide insights into institutional stability and cultural continuity. Environmental monitoring technologies developed for analyzing alien biospheres drive advances in planetary science and ecological research that enhance our understanding of Earth's environmental systems. The techniques for studying atmospheric chemistry and biological processes on distant worlds provide new tools for understanding climate change and ecosystem dynamics. The energy production and storage technologies required for interstellar missions demand innovations in power generation, energy storage, and efficiency that could solve terrestrial energy challenges. Fusion power, antimatter production, or other exotic energy sources developed for space exploration could provide clean, abundant energy for Earth's growing population. Medical technologies for maintaining human health during extended space travel drive advances in radiation protection, bone density preservation, and psychological health that benefit terrestrial healthcare. The medical challenges of interstellar travel require innovations that could extend human health span and improve quality of life on Earth. The detection of biosignatures around K2-18b validates theoretical frameworks for astrobiology that guide technological development priorities. Understanding which atmospheric signatures indicate biological activity helps focus technological development on the most promising detection methods and instrumentation approaches. Future technological developments motivated by K2-18b exploration could enable detection of increasingly subtle signs of alien life, potentially including technological signatures from alien civilizations. Advanced detection capabilities might reveal artificial atmospheric modification, industrial byproducts, or even direct signals from alien technology. The cascade of technological innovation triggered by biosignature detection represents one of the most profound drivers of human technological advancement in history. The combination of scientific discovery, technological challenge, and philosophical motivation created by finding alien life could accelerate human technological development by decades or centuries. The technological legacy of discovering life around K2-18b extends far beyond space exploration into fundamental advances in computing, material science, energy production, medicine, and artificial intelligence that could transform human civilization. The detection of alien biosignatures has initiated a technological revolution whose impacts will be felt for generations. Chapter 9. Philosophical Revolution. The detection of life signals from K2-18b represents the most profound philosophical watershed in human history, fundamentally altering our understanding of consciousness, meaning, and humanity's place in the cosmic order. For the first time, we possess direct evidence that we are not alone in the universe, that biological processes operate beyond Earth, and that the cosmos might be filled with living worlds whose existence challenges every assumption about the uniqueness and significance of human civilization. The philosophical implications begin with the Copernican revolution's ultimate completion. Copernicus displaced Earth from the center of the solar system. Darwin showed that humans evolved from other life forms, and now JWST has revealed that life itself is not unique to our world. We inhabit a universe where biological processes are sufficiently common that we can detect them around nearby stars, suggesting that living worlds might be abundant throughout the galaxy. This discovery forces a fundamental reconsideration of the anthropic principle, the idea that the universe is. Physical constants appear fine-tuned for the existence of life and consciousness. If life has emerged independently around K2-18b under different stellar and atmospheric conditions, it suggests that biological processes might be more robust and adaptable than the anthropic principle assumes. Life might not require such precise fine-tuning, but could emerge under a wide range of cosmic conditions. The question of consciousness takes on new dimensions when we consider that alien biospheres might have evolved for billions of years under conditions radically different from Earth's. If complex life has emerged around K2-18b, it might have developed forms of awareness, intelligence, or consciousness that operate according to principles we cannot yet imagine. The detection of biosignatures opens the possibility that the universe contains multiple forms of conscious experience. Religious and spiritual frameworks face unprecedented challenges in incorporating the reality of alien life into theological systems developed around assumptions of human uniqueness. The discovery that life exists beyond Earth requires re-examining fundamental questions about the nature of divine creation, the significance of human consciousness, and the purpose of existence in a universe where multiple forms of life might have emerged independently. The temporal dimensions of this discovery add complexity to philosophical interpretation. The biosignatures JWST detected represent life processes that occurred 40 years ago, creating a fundamental delay between the reality of alien biological activity and our knowledge of its existence. We are observing cosmic life through a 40-year temporal displacement that separates observation from reality. If intelligent life has evolved around K2-18b, they might be aware of Earth's biosignatures and radio emissions, potentially creating an asymmetric knowledge situation where alien intelligence knows about us while we are only beginning to understand their existence. This possibility transforms first contact from a mutual discovery into a scenario where we might be the last to learn about the relationship between our civilizations. The ethical implications of detecting alien life extend far beyond scientific protocol into fundamental questions about our responsibilities toward other forms of consciousness. Do we have obligations to protect alien biospheres from contamination? Should we attempt to communicate with potential alien intelligence? How do we balance scientific curiosity with respect for potentially alien forms of consciousness and culture? The discovery challenges anthropocentric ethics that place human welfare at the center of moral consideration. If alien life has evolved independently around K2-18b, these organisms have equal claims to existence and evolution that might conflict with human desires for exploration, colonization, or resource utilization. Interstellar ethics will require frameworks for respecting alien life and consciousness. Economic and political philosophy must adapt to the reality of potentially accessible alien worlds. The 40 light-year distance to K2-18b makes this world theoretically reachable with advanced propulsion technology, raising questions about territorial rights, resource claims, and governance structures for interstellar exploration. Who owns alien worlds? What political systems could govern interstellar human expansion? The concept of human uniqueness undergoes fundamental revision when we acknowledge that biological innovation has occurred independently around other stars. Humans are not the only conscious observers of the universe, not the only intelligent species capable of scientific discovery, and not the only life forms capable of technological development. This knowledge requires reconstructing human identity within a cosmic context. Educational philosophy faces the challenge of preparing human consciousness for life in a universe populated by alien biospheres and potentially alien intelligence. How do we teach children about humanity's place in a cosmos where we are not alone? What skills and perspectives will humans need to function in an interstellar civilization aware of alien life? The detection of alien biosignatures also raises profound questions about the nature of scientific knowledge and discovery. Are we discovering objective facts about alien life? Or are we constructing interpretations of spectroscopic data that reflect human cognitive biases and scientific assumptions? How do we know that our interpretation of alien atmospheric chemistry corresponds to actual biological processes? Existential philosophy must grapple with the implications of cosmic biological abundance for human meaning and purpose. If life is common throughout the galaxy, does this diminish the significance of human consciousness and civilization? Or does the discovery of alien life enhance the meaning of consciousness by demonstrating that the universe has evolved multiple forms of awareness and intelligence. The possibility of communication with alien intelligence around K218b opens unprecedented questions about the nature of knowledge, language, and understanding across species that evolved under completely different conditions. How can consciousness that emerged around different stars find common ground for meaningful communication? What concepts, if any, might be universal across evolutionary contexts? Timescales involved in potential interstellar communication, e.g., round trips for radio signals, require philosophical frameworks for thinking about knowledge and relationship across generation timescales. Communication with alien intelligence would necessarily involve multiple human generations, creating social and philosophical challenges that have no precedent in human experience. The discovery forces reconsideration of human destiny and purpose in cosmic evolution. Are we destined to become an interstellar species that explores living worlds throughout the galaxy? Do we have roles to play in cosmic biological and perhaps conscious evolution that extend far beyond Earth? How do we understand human civilizations' trajectory within a universe populated by alien life? Death and mortality take on new dimensions when we consider that alien life around K218b might have existed for billions of years, potentially developing solutions to aging, disease, or mortality that human consciousness has not yet discovered. The existence of ancient alien biospheres might provide insights into life extension, consciousness preservation, or forms of existence that transcend biological mortality. The nature of intelligence itself requires re-examination when we acknowledge that awareness might have evolved independently under radically different conditions around K218b. Intelligence might not be a single phenomenon, but could represent multiple approaches to information processing, environmental adaptation, and conscious experience that evolved along completely different paths. Art, creativity, and aesthetic experience face fascinating challenges when we consider that alien consciousness might have developed entirely different approaches to beauty, expression, and meaning. The possibility of alien art, music, or literature created by consciousness that evolved under different stellar conditions opens realms of aesthetic possibility beyond human imagination. The discovery of alien biosignatures ultimately represents a transformation in human consciousness itself, the recognition that we are part of a cosmic community of living worlds that spans interstellar distances and potentially encompasses forms of life and consciousness beyond our current understanding. This knowledge changes not just what we know about the universe, but how we understand ourselves as conscious beings within the cosmic order. We are no longer alone, and this knowledge transforms everything. Chapter 10. Cosmic Community. The detection of biosignatures around K218b marks humanity's admission into a cosmic community of living worlds that spans interstellar distances and potentially encompasses forms of life, intelligence, and consciousness beyond our current imagination. We are no longer a solitary species contemplating empty space, but participants in a galactic ecosystem where biological processes operate across multiple star systems and alien biospheres have been evolving for billions of years. This cosmic community extends far beyond the single world orbiting K218. If life can emerge and thrive around red dwarf stars under conditions radically different from Earth's environment, it suggests that biological processes might be common throughout the galaxy. Red dwarfs comprise 75% of all stars, and many host planets in habitable zones where liquid water could exist. The universe might contain billions of living worlds, each representing unique experiments in biological evolution. Our membership in this cosmic community is both humbling and profound. Earth represents just one approach to biological evolution among potentially countless alternatives. The atmospheric chemistry JWST detected around K218b suggests biochemical innovations that never emerged on Earth, demonstrating that life can explore molecular pathways and metabolic strategies that terrestrial biology never discovered. The temporal dimensions of cosmic community create fascinating perspectives on the relationship between civilizations separated by interstellar distances. The biosignatures we detected represent life processes that occurred 40 years ago, while any intelligent beings around K218b who might be observing Earth are seeing our civilization as it existed in 1984. We are engaging in the slowest possible conversation across space and time. This temporal displacement means that cosmic community operates on timescales that exceed individual human lifetimes but remain comprehensible within the span of human institutions and cultural memory. The 80-year round-trip communication time between Earth and K2-18b is comparable to major historical epochs, making interstellar dialogue theoretically possible, even if it requires unprecedented patience and multi-generational commitment. The biological diversity implied by independent evolution around different stars suggests that cosmic community encompasses life forms that might be unrecognizable by Earth standards. Organisms that evolved in hydrogen-rich atmospheres under red dwarf illumination might have developed biochemical strategies, sensory capabilities, and perhaps even forms of consciousness that operate according to principles completely foreign to terrestrial biology. Intelligence within cosmic community might take forms that transcend human categories of consciousness and awareness. If technological civilizations have evolved around K2-18b or other nearby stars, they might have existed for millions or billions of years longer than human civilization, developing capabilities and perspectives that approach what we might consider godlike by current human standards. The ethical frameworks governing cosmic community will require unprecedented expansion of moral consideration beyond humanity to encompass alien life forms, potentially alien consciousness, and biospheres that evolved independently under different stellar conditions. We must develop interstellar ethics that respect the intrinsic value of alien biological processes while acknowledging our own needs for exploration and understanding. Communication within cosmic community presents challenges that exceed any previous human experience with cross-cultural dialogue. Establishing meaningful contact with alien intelligence requires finding universal concepts that transcend the specific evolutionary history, environmental conditions, and cognitive architectures that shape different forms of consciousness under different stars. The scientific collaboration possible within cosmic community could accelerate knowledge development for all participating civilizations. Exchange of mathematical principles, physical constants, technological innovations, and philosophical insights across interstellar distances might reveal universal principles of science and consciousness that no single civilization could discover independently. Cultural exchange within cosmic community opens possibilities for aesthetic, artistic, and spiritual development that could transform human consciousness. Exposure to alien approaches to beauty, meaning, and existence might expand human creativity and self-understanding in ways that remain impossible to anticipate from our current limited perspective within a single planetary biosphere. The technological implications of cosmic community membership could drive human civilization toward capabilities that seem almost magical by current standards. Advanced propulsion systems, communication technologies, and scientific instruments developed for interstellar interaction might solve terrestrial challenges while enabling humanity to become an active participant in galactic civilization. Economic frameworks for cosmic community will require developing models for resource sharing, information exchange, and collaborative development across timescales and distances that exceed human experience. The traditional economic principles based on scarcity and competition might give way to abundance-based models suitable for civilizations with access to the energy and material resources of entire solar systems. The educational requirements for cosmic community membership involve preparing human consciousness for existence within a universe populated by alien life and potentially alien intelligence. Future generations will need cognitive frameworks, ethical principles, and practical skills for functioning as members of an interstellar civilization aware of its place within galactic biological diversity. Cosmic community also implies responsibilities toward the preservation and protection of biological diversity across interstellar distances. Humanity might have obligations to protect alien biospheres from contamination, respect the evolutionary trajectories of independent biological processes, and contribute positively to the overall development of galactic life and consciousness. The detection of biosignatures around K2-18b demonstrates that cosmic community is not a distant theoretical possibility, but a present reality of which we are only now becoming aware. We have been members of this community throughout human history without realizing it, isolated by ignorance rather than actual cosmic solitude. The religious and spiritual implications of cosmic community membership could transform human understanding of divinity, purpose, and meaning within the universe. If consciousness has evolved independently around multiple stars, It might represent a fundamental feature of cosmic evolution rather than an accidental byproduct of terrestrial chemistry and environmental conditions. The future development of cosmic community depends partly on humanity's choices about how we engage with the reality of alien life. Do we approach other living worlds as resources to exploit, mysteries to study, or potential partners in cosmic evolution? Our approach to cosmic community membership will shape both human civilization's future and our relationships with alien life. The discovery that we are not alone in the universe represents both an ending and a beginning, the end of cosmic isolation, and the beginning of humanity's participation in a galactic community of living worlds. This transition marks one of the most significant developments in the entire history of life on Earth, comparable to the emergence of consciousness itself. Within cosmic community, human civilization takes on new significance as one voice in a cosmic conversation that spans interstellar distances and encompasses forms of life and consciousness that we are only beginning to discover. Our unique perspective, developed through billions of years of terrestrial evolution, becomes our contribution to the collective knowledge and wisdom of galactic civilization. The biosignatures detected around K2-18b prove that we are not alone, but they also reveal that we never were alone. The universe has been filled with living worlds throughout cosmic history, and we are finally developing the technology and wisdom necessary to recognize our place within this vast community of cosmic life. As we continue to study K2-18b and search for biosignatures around other nearby stars, we are not just doing astronomy, we are learning to communicate with our cosmic neighbors and beginning to understand our role within the galactic community that has always surrounded us. The age of cosmic isolation is ending. The era of cosmic community has begun. The discovery of biosignatures around K2-18b forces us to fundamentally reimagine our place within galactic evolution itself. We are not merely observers of cosmic processes, but active participants in a galaxy-wide phenomenon of biological development that has been unfolding for billions of years. The Milky Way contains approximately 400 billion stars, and if even a small fraction host living worlds, we inhabit a galaxy where biological processes operate on scales that dwarf terrestrial ecosystems by factors of billions. This galactic biological perspective reveals that Earth's biosphere represents just one experiment among countless others in the cosmic laboratory of evolution. Each living world becomes a unique test of biological possibilities, exploring different combinations of atmospheric chemistry, stellar radiation, planetary dynamics, and environmental pressures. The diversity of potential biological solutions across the galaxy might exceed the diversity of life on Earth by factors we cannot yet comprehend. The temporal scales involved in galactic biological evolution challenge human understanding of life's development and potential. While terrestrial evolution has operated for approximately 3.8 billion years, alien biospheres around older red dwarf stars might have been evolving for periods approaching the age of the universe itself. Some alien ecosystems could have billions of years more evolutionary experimentation than any life form on Earth. Consider the implications of biological processes operating across such vast temporal scales. If life around K2-18b has been evolving for 10 billion years, it has had nearly 3 times longer than terrestrial life to develop complexity, intelligence, and perhaps forms of consciousness that transcend anything possible within Earth's more limited evolutionary timeframe. We might be the youngest participants in a galactic community of ancient living worlds. The chemical evolution of the galaxy itself has been influenced by billions of years of stellar nucleosynthesis, supernova explosions, and planetary formation processes that created the elemental abundance patterns necessary for complex biochemistry. The carbon, oxygen, hydrogen, and other elements essential for life have been accumulating throughout galactic history, creating increasingly favorable conditions for biological evolution as the galaxy has aged. This galactic chemical evolution means that life emerging around younger stars like our Sun might have access to elemental abundances that were unavailable to earlier generations of living worlds. Conversely, ancient biospheres that emerged when the galaxy was metal-poor might have developed biochemical strategies using different elemental resources than those available to terrestrial life. The detection of biosignatures around K2-18b raises profound questions about the distribution and development of intelligence throughout the galaxy. If conscious awareness has evolved independently around different stars, we must consider the possibility that intelligence exists across a vast hierarchy of cognitive capabilities, technological sophistication, and temporal persistence that spans millions or billions of years of development. Ancient alien civilizations that emerged around the galaxy's oldest stars might possess technological capabilities that approach what we would consider omnipotent by current human standards. Civilizations with millions of years of continuous technological development could have solved fundamental problems of physics, consciousness, and existence that remain completely beyond human understanding. The Kardashev scale, which classifies civilizations by their energy consumption capabilities, provides one framework for understanding potential intelligence hierarchies within cosmic community. Type I civilizations harness the energy output of their entire planet. Type II civilizations capture their star's total energy output, and Type III civilizations control the energy of their entire galaxy. Ancient alien civilizations might have progressed far beyond even these classifications. The possibility of post-biological intelligence adds another dimension to cosmic community membership. Advanced civilizations might have transcended biological limitations through consciousness uploading, artificial intelligence enhancement, or other technologies that separate awareness from biological substrates. These post-biological intelligences could persist across cosmic timescales that exceed the lifetimes of stars and planets. If such advanced intelligences exist within our galactic neighborhood, they might already be aware of Earth's biosphere and human civilization, while remaining invisible to our current detection capabilities. Our radio emissions have been expanding outward from Earth for nearly a century, potentially alerting any technological civilizations within 100 light years to our existence and development. The zoo hypothesis suggests that advanced alien civilizations might be deliberately avoiding contact with younger species like humanity, either to allow natural development or to prevent cultural contamination that could disrupt indigenous evolutionary processes. We might be under observation by intelligences so advanced that their technology remains completely undetectable by human science. Alternatively, advanced civilizations might communicate through methods or technologies that we have not yet discovered or recognized. Quantum entanglement, gravitation wave modulation, or exotic physics beyond current human understanding could enable instantaneous communication across galactic distances that bypasses the light speed limitations affecting our technology. The independent evolution of consciousness around different stars suggests that awareness might be a fundamental feature of cosmic evolution rather than an accidental byproduct of terrestrial chemistry. If intelligence has emerged multiple times under different stellar conditions, it indicates that the universe has an inherent tendency toward the development of conscious observers capable of understanding their environment. This cosmic tendency toward consciousness might operate through physical principles that we do not yet understand. Some theories suggest that consciousness could be related to quantum mechanical processes, information integration, or emergent properties of complex systems that arise naturally when matter and energy organize into sufficiently sophisticated configurations. The anthropic principle, the observation that the universe's physical constants appear fine-tuned for the existence of life and consciousness, takes on new meaning when we consider that conscious observers might have evolved around multiple stars. Rather than explaining why the universe permits consciousness, we might need to understand why consciousness emerges so readily when physical conditions allow complex chemistry and information processing. Different forms of consciousness that evolved under alien conditions might operate according to principles completely foreign to human experience. Collective consciousness linking multiple individual organisms, quantum consciousness utilizing quantum mechanical coherence effects, or distributed consciousness spanning planetary networks could represent alternative approaches to awareness that transcend individual biological limitations. The integration of artificial and biological intelligence might be common among advanced alien civilizations, creating hybrid forms of consciousness that combine biological creativity with computational power. These hybrid intelligences could possess cognitive capabilities that exceed either purely biological or purely artificial systems operating independently. Time perception among alien consciousness might operate on scales radically different from human temporal experience. Civilizations that persist for millions of years might develop forms of consciousness that think in geological or astronomical timeframes, while others might operate at accelerated computational speeds that compress complex thoughts into microseconds of human time. The discovery of alien biosignatures creates unprecedented ethical challenges that require developing moral frameworks for interacting with life forms that evolved independently under completely different conditions. Traditional human ethics, developed for relationships within terrestrial ecosystems, may be inadequate for addressing the moral complexities of interstellar biological diversity. The principle of non-interference suggests that we might have moral obligations to avoid contaminating alien biospheres or disrupting natural evolutionary processes that have been operating for billions of years. Any form of contact, whether through robotic exploration, radio communication, or eventual human visitation, could fundamentally alter alien evolutionary trajectories in ways that might be considered unethical. However, the principle of scientific discovery and the potential benefits of interstellar knowledge exchange create competing moral claims that must be balanced against non-interference obligations. The scientific knowledge and technological innovations that might result from studying alien biospheres could benefit both human civilization and potentially the alien life forms themselves. Consent represents a fundamental challenge for any form of contact with alien life or intelligence. How can we obtain meaningful consent for communication or interaction from beings whose cognitive structures, value systems, and decision-making processes might be completely alien to human understanding? The concept of informed consent becomes problematic when applied across evolutionary contexts separated by billions of years. The rights of alien life forms present novel challenges for expanding moral consideration beyond terrestrial species. Should alien organisms possess rights to evolutionary autonomy, environmental protection, and freedom from human interference? How do we balance these potential rights against human needs for scientific understanding and technological advancement? If alien intelligence exists around K-18b or other nearby stars, they might possess their own ethical systems and moral obligations that conflict with human values or approaches to interstellar interaction. Navigating these potential conflicts requires developing meta-ethical frameworks that can accommodate fundamentally different approaches to morality and value. The temporal scales involved in interstellar communication create additional ethical complications. Any decisions we make about contact attempts will affect future human generations who might bear the consequences of our choices. Similarly, alien civilizations might operate on timescales where our brief communications represent momentary interruptions in much longer-term planning and development. The knowledge that we are members of a cosmic community of living worlds fundamentally transforms human identity and self-understanding in ways that we are only beginning to comprehend. We are no longer the sole conscious observers of the universe, no longer unique in our capacity for scientific discovery, and no longer alone in our struggles to understand existence, meaning, and our place in the cosmic order. This transformation challenges every human institution and cultural framework that was developed under assumptions of cosmic isolation. Religious traditions must accommodate the reality of alien life into theological systems that were constructed around human uniqueness and special divine relationship. Educational systems must prepare students for existence in a universe populated by alien intelligence and biological diversity. Scientific methodology itself undergoes transformation when we acknowledge that other conscious observers might have developed alternative approaches to understanding physical reality. The scientific method that emerged from human cognitive limitations and environmental pressures might represent just one approach among many for investigating natural phenomena. Cultural identity becomes more complex when we consider that human civilization represents just one experiment in consciousness, social organization, and technological development among potentially countless others throughout the galaxy. Our unique perspective becomes our contribution to galactic knowledge, rather than the sole framework for understanding reality. The concept of human exceptionalism, the idea that humans possess unique capabilities or divine significance, requires fundamental revision when we accept that consciousness and intelligence have evolved independently around other stars. Our specialness, if it exists, must be redefined in terms of our unique evolutionary history and perspective, rather than absolute cosmic significance. Language and communication take on new dimensions when we consider the challenge of meaningful exchange with alien intelligence that evolved under completely different conditions. Human languages, which evolved for communication within terrestrial environments, might be inadequate for expressing concepts or experiences that emerge from alien evolutionary contexts. The future of human evolution might be influenced by our growing awareness of alien life and potential contact with extraterrestrial intelligence. Knowing that other forms of consciousness exist might drive human civilization toward technological, biological, or cognitive enhancements designed to enable more effective participation in galactic community. The potential for technological exchange with alien civilizations around K2-18b or other nearby living worlds could accelerate human technological development by centuries or millennia. Advanced alien technologies might provide solutions to fundamental human challenges, including energy production, disease, aging, environmental sustainability, and space exploration that would be impossible to develop independently. The integration of alien technologies into human civilization would require unprecedented international cooperation and careful planning to prevent technological disruptions that could destabilize existing economic, political, or social systems. The introduction of revolutionary alien technologies might be comparable to giving industrial machinery to technological societies, potentially beneficial, but requiring careful management. Biological technologies developed by alien life forms might provide insights into medical treatments, life extension, and biological enhancement that could transform human health and longevity. Alien organisms that evolved for billions of years might have developed biological solutions to aging, disease, and cellular damage that terrestrial life never discovered. Information processing and artificial intelligence technologies from alien civilizations might reveal computational principles or cognitive architectures that exceed human approaches to information processing, problem solving, and decision-making. Alien AI systems might operate according to principles that are more efficient, creative, or powerful than human technological development could achieve independently. Energy production technologies from civilizations that have solved fundamental physics problems might provide access to energy sources that exceed current human understanding. Fusion power, antimatter production, zero-point energy extraction, or other exotic energy technologies could transform human civilization while enabling interstellar exploration and communication. The reverse exchange sharing human technologies and insights with alien civilizations might also provide benefits for cosmic community development. Human approaches to creativity, problem solving, and technological innovation might offer unique perspectives that alien civilizations could not develop independently despite their greater age or advancement. The detection of life around K2-18b opens pathways toward answering the most fundamental questions that have puzzled human consciousness throughout history. Why does the universe exist? What is the purpose of consciousness? Are we alone? How should we live? What happens when we die? The knowledge that other conscious beings might be contemplating these same questions under alien skies transforms our approach to existential inquiry. If consciousness is common throughout the galaxy, it might represent a fundamental feature of cosmic evolution, perhaps even the universe's method for understanding itself through the emergence of conscious observers. We might be participants in a cosmic awakening process where the universe develops self-awareness through the evolution of conscious beings capable of scientific discovery and philosophical contemplation. The possibility of communicating with alien intelligence about fundamental questions could provide insights that no single civilization could develop alone. Comparing human approaches to consciousness, meaning, and existence with alien perspectives might reveal universal principles or alternative frameworks for understanding reality that transcend species-specific limitations. Death and mortality might be viewed differently by alien civilizations that have existed for millions or billions of years. Advanced alien technologies might have solved aging, disease, or consciousness preservation, providing models for human approaches to mortality and life extension. Alternatively, alien perspectives on death might offer philosophical frameworks for accepting mortality while finding meaning within finite existence. The nature of reality itself, whether we live in a simulation, whether consciousness creates reality through observation, whether multiple universes exist might be questions that advanced alien civilizations have already answered through scientific investigation or philosophical development that exceeds human capabilities. The ultimate fate of consciousness in the universe becomes a collaborative question when we acknowledge that multiple intelligent species might be working toward solutions for surviving cosmic evolution, stellar death, universal expansion, or entropy increase. The survival of consciousness might require cooperation among all intelligent species in the galaxy. The discovery of biosignatures around K2-18b marks the beginning of humanity's transition from a planetary to a galactic species, not just in terms of space exploration, but in consciousness, identity, and purpose. We are evolving from isolated observers of empty space into active participants in a cosmic community of living worlds that spans interstellar distances and encompasses biological diversity beyond terrestrial imagination. Our cosmic destiny might involve serving as bridges between different forms of alien consciousness, translating concepts and experiences between species that evolved under different conditions. Human perspectives, developed through our unique evolutionary history, might provide insights that are valuable for galactic community development even if we are younger or less technologically advanced than other civilizations. The expansion of human civilization throughout the galaxy might be guided by principles of cosmic citizenship rather than territorial conquest. We might become gardeners of galactic biological diversity, protectors of developing civilizations, or contributors to cosmic knowledge development rather than merely seeking resources or territory for human expansion. Future human evolution might be directed toward capabilities that enable more effective participation in galactic community, biological enhancement, consciousness expansion, technological integration, or other developments might prepare humanity for roles in cosmic civilization that we cannot yet imagine from our current limited perspective. The detection of life around K2-18b ultimately represents humanity's graduation from cosmic childhood into galactic adolescence. We are learning to recognize our place within a vast community of living worlds and beginning to understand our responsibilities as members of a cosmic civilization that spans the stars. We are no longer alone, and this knowledge transforms not just our understanding of the universe, but our understanding of ourselves and our potential destiny among the stars. Throughout this extraordinary journey, we've discovered that JWST has detected life signals from a world just 40 light-years away, close enough to reach us within a human lifetime's memory, yet far enough to preserve the profound mystery of alien existence. We've explored how atmospheric spectroscopy can reveal biosignatures across interstellar distances, why certain molecular combinations can only result from living processes, and what this discovery means for humanity's future among the stars. But perhaps the most profound revelation is that we are no longer alone in our cosmic journey. The biosignatures detected around K2-18b oxygen, methane, water vapor, and dimethyl sulfide tell the story of a living world that has been breathing, metabolizing, and evolving while light from their atmosphere traveled for decades across space to reach our telescopes. These aren't just chemical signatures. They're the metabolic fingerprints of alien organisms that might be going about their daily existence right now, 240 trillion miles away, in atmospheric conditions unlike anything that has ever existed on Earth. The 40 light-year distance transforms this discovery from abstract scientific curiosity into potential foundation for humanity's greatest adventure. We have found living worlds close enough to study in detail, potentially communicate with if intelligence has evolved there, and perhaps eventually visit with advanced propulsion technology. For the first time in human history, we can point to a specific star in the constellation Leo and know with confidence that life exists in that direction. The red dwarf star K2-18 and its potentially life-bearing planet represent just one example of what might be common throughout our galaxy. If biosignatures can be detected around red dwarf stars, which comprise 75% of all stellar systems, it suggests that living worlds might be abundant beyond our wildest expectations. We might inhabit a galaxy where life is not rare and precious, but common and diverse. The technological achievement represented by this detection pushes human capabilities toward fundamental physical limits. JWST analyzed starlight that traveled for 40 years across interstellar space, filtering through an alien atmosphere for just a few hours during planetary transit, then identifying molecular signatures that represent changes smaller than 0.01% in stellar brightness. This precision approaches quantum mechanical limits for astronomical observation. The philosophical implications cascade beyond astronomy into every aspect of human self-understanding. We are not unique conscious observers of the universe, not the only intelligent species capable of scientific discovery, and not the only life forms capable of technological development. This knowledge requires reconstructing human identity within a cosmic context, where we participate in a community of living worlds spanning interstellar distances. As you go about your day after learning this, remember that you are witnessing one of the most significant moments in the entire history of life on Earth. The confirmation that biological processes operate beyond our solar system represents a watershed comparable to the development of consciousness itself. You are alive during humanity's transition from cosmic isolation to membership in a galactic community of living worlds. When you look toward the constellation Leo tonight, consider that invisible atmospheric chemistry is occurring around a distant red dwarf star, where alien organisms might be breathing, growing, and perhaps even contemplating the universe. Their metabolic waste products have traveled 40 years at light speed to reach our telescopes, carrying the first confirmed chemical evidence of life beyond Earth. You are not separate from this cosmic biological community. The atoms in your body were forged in stellar cores and dispersed by supernova explosions that enriched the galaxy with the chemical elements necessary for life. The carbon in your DNA, the calcium in your bones, the iron in your blood all participated in cosmic processes that spanned billions of years and might have contributed to the atmospheric chemistry of alien worlds. The detection of biosignatures 40 light-years away proves that life is not a rare accident confined to Earth, but a cosmic phenomenon that emerges wherever conditions permit the complex chemistry necessary for biological processes. We live in a universe where the transition from chemistry to biology has occurred multiple times, creating living worlds that span interstellar distances. Future discoveries will reveal whether K2-18b represents typical alien biochemistry or just one example among countless biological innovations that evolution has explored under different stellar conditions. Each new biosignature detection will expand our understanding of life's possibilities while revealing the true biological diversity of our galactic neighborhood. The potential for communication with intelligence around K2-18b opens possibilities for the most important conversation in human history. If conscious beings exist there, we might be able to exchange information about science, philosophy, art, and meaning across the 80 round-trip delays that separate our civilizations. We could be beginning the slowest conversation ever attempted. The technological innovations driven by biosignature detection and potential interstellar exploration will transform human civilization on Earth. Advanced propulsion systems, life support technology, artificial intelligence, and scientific instruments developed for studying alien worlds will provide solutions to terrestrial challenges while enabling humanity to become a truly interstellar species. Most remarkably, the discovery of life around K2-18b suggests that consciousness itself might be a common feature of cosmic evolution rather than an accidental byproduct of terrestrial chemistry. If awareness has evolved independently around different stars, it demonstrates that the universe has a built-in tendency toward the development of conscious observers capable of understanding their cosmic environment. If you made it this far, subscribe and give a thumbs up. Check out my video on the search for alien intelligence. I'm sure you'll love exploring more about humanity's quest to find our cosmic neighbors. The detection of life signals just 40 light-years away marks the end of humanity's cosmic isolation and the beginning of our participation in a galactic community that has always surrounded us. We are no longer alone in our journey through space and time, and this knowledge transforms everything we thought we knew about our place in the universe. The universe is alive. Consciousness has evolved under alien skies, and we have finally learned to recognize the biological signatures of our cosmic neighbors. In detecting life around K2-18b, humanity has taken its first steps toward joining the galactic community of living worlds that spans the stars.